Here we go. Lesson 3. Applications of magnetic forces and right-hand rules. One really cool application is revisiting the TV, the cathode ray tube, and I would love to spend more time on it, but Ange, I'm going to say, I got to nuke it right now. So you can cross that out. You can cross that out. You can cross out example 1. You even cross out example 2. Lyndon, I gave you another lesson. That's for later. All right. But this application I'm absolutely going to be quizzing or assessing you on. Here's how electric motors work. We're going to be using our right-hand rule. You can use the screen behind me, or you can hold your piece of paper up vertically if you want to. I'd like you to imagine that we have a rigid coil of wire. Now, Lena, in real life, what we do is we have hundreds and hundreds and hundreds of coils of wire, but we're just going to look at a single wire. And I'm calling it a coil, even though it's square-shaped, just so that I made it square-shaped so it's easier for us to follow. Okay. Here is my magnetic field. Which way is my magnetic field pointing? To the... Okay? And if you look at the battery, here's what's happening. Charges are flowing this way. Draw this in. This way. Then I have a section right where the number 1 is, where the charges are flowing to the left. I have a section where the number 2 is, where charges are flowing to the straight up. I have a section where number 3 is, where the charges are flowing that way, and that way. What's going to happen here? Well, moving charges, when they move through a magnetic field, will experience a force. They'll only experience a force, though, when they're cutting across the magnetic field lines. This here will not feel it, don't circle that, will not feel a force at all. And you can try that, because if I use my right-hand rule, if I point my right hand to the right and I try to extend my fingers in the same direction as the magnetic field, I'm now suddenly doing this, and I've told you the right-hand rule is always like you're going to high-five with your thumb sticking out. So the fact that I'm having to bend like this, there's no force being exerted on the top chunk of wire on chunk number 3. And the same goes for chunk number 1. But chunk number 2 and chunk number 4. Let's look at chunk number 2. If I point my thumb up my page, or with the screen, which way is the magnetic field pointing? To the right. So I point my hand to the right. Which way is my palm pointing? Wire section number 2 is going to feel a force into the page. And remember, that's how we draw into the page. It's the tail feathers of an arrow going away from us. To the right. Oh, you already doing number 4?
No, I've tried like the question.
Oh, we're getting there. Okay, right-hand rule questions. We're going to be practicing the right-hand rule an awful lot in the next few days as well. It'll help you become clearer. Look at section number 4. Now, Lena, you're correct. It's moving down the page. Magnetic field is still pointing to the right. When I bend my hands and kind of do a yoga move, I end up with my palm pointing out of the page. This section of wire is going to feel a force out of the page. And what that means is this is going to spin. Try it sometime, but if you have any kind of a square, if you push down on one side and lift up on the other side, it's going to spin. It's going to spin. Lyndon, you're using your right-hand rule, not flexing, but good try. Okay? So let's fill in these questions here. It says, the direction on the magnetic force on segment 1, there's none, because for you to experience a force, you have to cut across the magnetic field lines. You don't run parallel to the magnetic field lines. And the same goes for the direction on line 3. There's none. But what's the direction of the magnetic force on segment 2? What did we say the force was? So D. Out of the page for segment 4. Will the loop tend to rotate? Yeah. Which direction? Well, it depends which way you're looking at it. But if you were standing on the battery looking at it, you would see the loop rotate into the counterclockwise. Will the loop tend to rotate? Yes. Which direction? Depends where you're standing. We'll get to that in a second. The problem with this setup is as soon as it does half a rotation, you'll end up with wire 2 on the right, and you'll end up with wire 4 on the left, and it'll come to a crashing stop because now this wire here is feeling a force into the page, and this wire here is feeling a force out of the page. If you look up for a second, I'll use this roll of tape as my coil of wire analogy here. And what would happen really quickly, it would feel a force, but then right away, this is now pushed this way, and this is pushed that way, it would come to a stop. So what we have to come up with, Kevin, is some kind of an easy way where we can have it spin continuously so that on the left-hand side, the current is always flowing up the page, so that when wire 4 gets to here, somehow we manage to flip the current. And on the right-hand side, current is always flowing down the page, so that when wire 2 gets to this side, it somehow flips the current. We can do that. We're clever. Do you see how, though, we can get something to start to spin? This is a motor, an electric motor. This is what drives electric cars. This is what causes electric tires to spin, all that stuff. Okay? So here is a simple one-turn coil motor. And what we do to get the current to automatically rotate or flip or spin or change direction on its own is we actually have, you can imagine, 2 sort of hamburger buns on the end with no patty in the middle. We have a little gap right here. And what we have are some brushes right here so that as the motor spins, when this wire gets to this side, the current will now be flowing this way. When this wire gets to this side, the current will now be flowing that way. Let me walk you through it all. It's going to be complicated, but it'll make sense. Trust me. Okay? So read along with me. It says this. The coil in the motor is called the armature. That's a word I'm going to use. The armature is the thing that spins inside of the motor, and then you hook the armature up to an axle or to a toy or to whatever it is that you want to fan, whatever. Okay? Of course, a real motor will have many turns of wire. If you have 2 turns of wire, your motor is twice as powerful. If you have 5 turns of wire, your motor is 5 times as powerful, so you can control the power of the motor very easily. Also, the external magnet may be an electromagnet rather than a permanent magnet, but we're using ones with permanent magnets for ease of figuring this out. It says, note the importance of the split ring commutator. Say, what? So, right now, we have the current flowing into the page on the left. Which way do magnetic field lines point from what to what? So if I draw a magnetic field pointing that way, and I point my thumb into the page, put your phone away, Caleb. Point my thumb into the page. The left side of this wire is going to feel a force in which direction? You're not curling your hand, hands flat. Right? This is the right hand rule. Kieran, don't do that. You'll get the wrong answer. Hands flat. So if I stand up, if you hold your paper like this, I would go like that, like that. Which way is this, the left-hand wire, going to feel a force? Down. Which way will the right-hand wire feel a force? And so it's going to start to spin. The problem is, if this now got to that side, it would feel a force up, so it would start to spin this way, and all that would happen is it would just go back and forth, back and forth. I don't want that, Lena. I want to get a continuous spinning motion. How can I do that then? What I do is I have what's called a split ring commutator. I put a gap right there. And what happens is the motor starts to spin. Its momentum carries it onto the spin. So it does about half the spin just with its own momentum. And then this little piece of metal gets to this side where the current is flowing this way. And this little piece of metal gets to this side where the current is flowing this way. And what we have are little metal brushes with very low friction that are transferring the current. Let me show you an animation. Yeah. So here's an animation. Unfortunately, I can't make it any larger, but what we have, if I just hit pause, the current is flowing this way, and that way. Magnetic field lines are pointing down. So if I go resume, pause. Right here, the current is flowing sort of up and to the right. So all of you, if you want to point your thumbs up and to the right, please. What direction is the magnetic field pointing in our three-dimensional diagram? That's these blue lines. So right now, you want to hold your hand like this, like that. Kevin, which way is that top bar going to feel a force? In that direction right there. There's the arrow. Okay? Which way is this bottom one going to feel a force? Follow current, follow current. On the bottom bar, now the current's coming out of the page towards me. Bend my hand kind of like this, a little awkward, but I can do it. It's going to feel a force this way. So the top bar is going to feel a force, let's call it into the screen. The bottom bar is going to feel a force out of the screen. It's going to spin. If I didn't have that gap there, if I didn't have these brushes there, I'd have a problem. But watch what happens if I let this run really, really slowly here. So I'm going to slow it down a little bit. Resume. Right there. No current is flowing, but its own momentum is continuing it to spin, is keeping it spinning. And now notice, if I pause right now, this bar here was on the bottom before, and before when it was on the bottom, the current was running out of the page towards us, but now it's on the top, and the current is running away from us. We've managed to flip the current cleverly without having any fancy schmancy mechanism by just allowing its own momentum to carry itself. This is called, this little setup right here is called a split ring commutator. And this is the basics of all motors. Now there's a problem with this, Kieran, and the problem is if you unplug the motor and it slowly spins to a stop, and it happens to stop right there, now when you plug it back in, the motor won't do anything. So in real life, and you don't need to know this, this is just purely for nerd trivia, instead of having a rectangular single armature, if you look at it from the end, what you'll actually have are three armatures at 120 degree angles from each other, and if you play around with it, you'll find there's no way that you can stop that motor without there being some net force on it when you power it back on again. So I'm giving you a very simplified version, but we can wrap our brain around this. Resume. I'll speed it up a little bit here. Okay. I'll turn stuff off. So here's the motor. Current flows like that. Magnetic field flows like that, and that gives us a magnetic force in that direction there. It's often called the Lorentz force. If I want to change direction, flip the current. Done. And we can do that with circuitry pretty easily. That's how an electric motor works. So, if we look at our notes again here, if we want a better motor, what we actually do is we make the armature a solenoid or a magnet as well. So now we've got two interacting magnetic fields, and that gives you a much more efficient motor. But again, you can see kind of the split ring commutator right there. I think I have a better diagram. Maybe I don't. Key idea, electric motors come in all sizes. Some are very tiny and drive toys. Others are huge and drive trains or buses. But this technology hasn't changed significantly. We've gotten better. The nice thing also with an electric motor is it's a completely sealed unit. You don't have to do oil changes. No dust can get in. You're not worried about having to put in filters or anything like that. They're really a nice setup. I'm very bullish on electric technology, if you hadn't figured that out by now. Okay? So now, if you'd be so kind as to get out lesson 1 that I handed out earlier, please. Voltage induced by motion. So, in the last couple of lessons, we learned that when you move electric charges, they produce a magnetic field, and a magnetic field will exert a force on moving charges. Early in the 19th century, scientists such as Michael Faraday and Joseph Henry were aware of these, and they asked the logical question. They said, look, if a current produces magnetism, can magnetism produce a current? Can we create electricity? And they were trying to design the generator. We're going to get to how a generator works in a second. Also recall that electromotive force, EMF, with that funky E symbol, it's an archaic word that refers not to a force but to the voltage in the cell. So we're going to use V and E interchangeably. They mean the same thing. So here's what Faraday and Henry played with initially. They said, suppose you have a conducting metal bar in a magnetic field. This magnetic field is into the page. You can no longer see the X's because this diagram has deteriorated. I apologize, but I'm telling you the magnetic field is into the page. And what we're going to do, Sarah, is we're just going to pull the bar down the page. Let's look at one charge. Everybody right now, put a little positive right in the middle, right there. Okay. Which way is the bar traveling? Down the page. So which way is the positive charge traveling? Since it's locked inside the metal bar, it's traveling down the page. Everybody point your right thumb down the page. What direction is the magnetic field? What does it say, Caleb?
Region of field into the page.
So point your right thumb down the page and point your fingers into the page.
It's feeling to the
What
right.
side of the bar will become positively charged? You're right, Caleb.
To the right.
What side of the bar will become negatively charged?
To the left.
So we've just figured out a way to separate charge, like in a battery, by moving something. Ooh. This side will become positive. This side will become negative. And since charges have been separated, and separating charges takes work, we have voltage, because voltage is work per coulomb, energy per coulomb. Joules per coulomb. We call this voltage induced voltage. Induced by motion. Because the energy in this case doesn't come from chemistry, like in a Duracell battery, but from motion. We say this is an induced voltage. In other words, motion can induce a voltage, an EMF. Let's see if we can find an expression for how much voltage moving a metal rod through a magnetic field can generate. What was the definition of voltage? Yep. That was, we said it was like voltage. Way back when, what was our definition of voltage from electrostatics?
The amount of potential.
Now, instead of potential energy, I'm going to think of that potential energy in terms of work done. Okay? Can you put it face down on the appropriate block, please? Thank you. And instead of using the V, because this is an induced voltage, I'll use the EMF because we're creating it. Work. What was our basic definition of work? Yep. Which force? A magnetic force on a charge. What was the magnetic force on a charge from last day? You want your formula sheet out, probably? Bill was on a wire. I want the magnetic force on a single charge.
It's QVB. QT.
Oh, that's kind of convenient. The Q cancels. Okay. And instead of D, we said because it's the length of wire, we often said we're going to use a lowercase l, and you get this. The EMF, the induced voltage, is equal to BLV, except all three of these need to be at right angles to each other. If they aren't, your right-hand rule doesn't work and you don't get an induced voltage. We'll look at that in a second as well. This is a scalar equation, although you can get a negative voltage. We'll talk about that later, but no direction. V or E is the voltage induced by motion, sometimes called motion EMF or induced EMF. B is the external magnetic field. L is the length of wire. V is the speed of wire, and perpendicular, we only get volts when they're perpendicular. If they're not perpendicular, we would use components, but I'm not going to dive into that this unit. If they're not perpendicular, we only get a tiny voltage. Look up. It says, indicate which end of the wire, turn the page. Indicate which end of the wire is negatively charged and discuss why little voltage is created. Which way is this bar moving? Still down the page. But you'll notice instead of having the bar oriented in that direction, I've rotated it 90 degrees. Let's do the same trick. Let's draw a little positive right there in the middle of the bar. Which way is the bar moving?
Down.
So which way is the positive charge moving?
Down.
Let's point our thumbs down. Which way is the magnetic field, Caleb?
To the left.
Which way is the magnetic field, Caleb?
Into the page.
So extend your right hands into the page. Caleb, I'm telling you to do it.
Yeah.
Which way is that positive going to feel a force?
To the right.
Here's the problem. Can it go anywhere to the right? Unlike the previous situation where I could separate the charges by some distance, is there any way for that positive to go to the right? And is there any way for the negatives to go to the left in this thin little chunk of metal? Lena, we just can't separate the charges with any type of distance. And so basically no voltage is going to be created, since there is no way to separate charges. Very little voltage is created. For all intents and purposes, zero. Example 4 says, find the induced voltage across the ends of the moving wire and indicate the polarity, which side of the wire is positive, which side of the wire is negative. Let's do that part first. Now let's decipher this diagram. I think this is the wire. What direction is the wire moving? Into the page. What direction is the magnetic field? So we'll do the same trick. Let's put a little positive in the center of the rod. I always draw that in because you know I like to write something down. I feel better. Which way is that positive charge moving? Which way is the wire moving? Which way is that positive charge moving? Into the page. So this time I'm not going to help you. And this time I'm going to say use your piece of paper. Point your right thumbs into the page. High five. Extend your fingers out. Which way is the magnetic field pointing? So Caleb is bending, or the other thing that Caleb could do is rotate his piece of paper 90 degrees. Okay? Or even rotate it 180 degrees if you need to.
It's to the left.
Is it? So all of you kind of try this, okay? And you have to, if I don't see you trying these, I will call you out because it's a disaster if you think, oh, Dewick is doing it and I can figure it out. You have to try your right-hand rule on your own. So if these were my notes, not the same notes that you have, but that's okay, I would be pointing my right thumb into the page. I would try and bend my hand down, which is a bit awkward. Now, wait a minute. Do that. That's a lot. In other words, move the paper to your right. Suddenly it's easier. I'm getting the positive side. My palm is pointing to the left. Is it not?
Yes.
Okay. So This end of the rod will be positive. This end of the rod will be negative. How many volts? Induced voltage is BLV. Pretty big magnetic field, although we've seen bigger. The length of the wire is 0.8, 5.25 meters per second. How many volts? And I think we're getting enough now to compete with a standard battery. 5.25?
Yeah.
Well, that's not bad.
It's the exact same number as the.
It's just because these two numbers happen to cancel each other out by a fluke. Okay.
I think not. That happens in every school.
That's not bad, though. 6-volt battery is what runs a golf cart.
Yes, it does.
5.25, that would certainly run a flashlight quite nicely. Now, if you've ever used a generator, you may have noticed, Mr. Dewick, I don't just move something to the right. I spin something. I turn a crank and something spins. We're going to get there. We'll explain how that works too. But this is where Faraday and Henry started out. They started saying, look, I can certainly see that this will create a voltage. This will induce a voltage. In fact, airplanes use this all the time. I don't know if they still do. I'm told back when they had smoking on flights, back when you had little push-in cigarette lighters that you would push them in, and after about 30 seconds they would pop out and glow red hot. I'm told that they got that voltage from this as follows. It says, find the motion voltage induced across the wings of an airplane and indicate the polarity. Okay. Well, there's a bit of a problem here. I didn't give you the direction of the magnetic field. So let's say that the magnetic field, because the airplanes are up fairly high, they're high enough that the Earth's magnetic field is curving back into the Earth, pointing down. Okay. Let's put a little charge right here in the middle of the airplane. Which way is that charge moving? Which way is the plane moving? So point your thumbs to the right. What direction is the magnetic field? What part of the plane will become positive? The top, the bottom, the back end, or the front end? In this picture, left wing. Yes?
Left wing.
That'll become positive. That'll become negative. How many volts are we going to generate here? Which L am I going to use, the 60 or the 150? Which one is at right angles to everything else? The 60, because the speed and the magnetic field and the length all have to be perpendicular to each other. So I'm going to use the 60. Ooh, that's much more substantial. That's more that's coming out of a power outlet. You got 154 volts?
Yes.
And that voltage is sitting there. Use it. So they do. I don't know what it powers now. My understanding is back in the old days it was what they would use to power the old cigarette lighters. Because they're making the assumption that all 300 or 200 passengers aren't going to push the lighter in all at the same time, and you can do that then with a nice trickle charge.
How did you find the polarity? Like with that, like,
Okay, so looking up here, I pointed my thumb this way. Magnetic field is into the page.
Yeah.
Which way is my palm pointing?
up.
The positives are going to get pushed to the top of the left wing. The negatives are going to get likewise pushed to the bottom of the right wing.
And how would that make the cigarette lighter?
Have we separated charges? So we now have a voltage. Now, it's a good question. Turn. If we then connect that moving metal strip to conducting rails, then the strip will act like a battery and we'll get current flow.
I'll just heat it up.
Well, yeah, like the same way your stove elements work, just on a lower. you folks have grown up, your cars did not all have cigarette lighters. So my generation, every car, I realized, yeah, the push one, you might have an older car that still has it, where you push it in, you wait, suddenly you pull it out, ooh, it's red hot. Those are the kind of cigarette lighters they used to have on airplanes as well, back when they had smoking on flights. I don't miss those days. So, it says this, show that the polarity of the moving wire strip below left is just like having a battery like that. Well, let's see. Let's put our little positive charge right there. And really what we're talking about in real life are trillions of positive charges all holding hands, metaphorically. Which way are they moving? So point your right thumbs to the right. What direction is the magnetic field in this region? So for me, I'm going to have to hold my hand on the board like this. If I was doing it on my piece of paper, I would go like this. But no matter what, it seems like I get current flowing this way. Positives flowing that way. Yes? And then when they hit this wire, they would go this way. And then they would be used to run this resistor. Maybe it's a light bulb. The light bulb would glow. And so I'm going to argue that mathematically, Sarah, it's the same as that circuit. But now, instead of a battery, it's an induced voltage source. We're going to continue with this idea of an induced voltage, but looking at what we've done so far for right-hand rule practice questions. So here, I'm not going to assign every one of these. You can cross out number 1, cross out number 2. I love number 3. I love number 3. Number 3, will you marry me? And what I mean by this is, if you're asking me, what am I going to assess you on in this unit? The whole idea of magnetic force pushing me in a circle. Okay? Lena, you know where we are yet or not? Okay. So you're looking for the ultimate electromagnetic forces assignment? Have you found it yet? You got it? So you can cross out 1, cross out 2. This idea of being pushed into a circle, but any one of those variables is fair game. I could ask you to find R, I could ask you to find the mass, I could ask you to find the speed, I could ask you to find the magnetic field required. Any of those variables would be fair game. So 3 is good. Right-hand rule questions. These will be questions on your final, absolutely conceptual. So 5 is good. You can skip 4. Six is good. 7 is good. Skip 8. 9 is good. 10 is good. Skip 11. 12 is good. 13 is good. Take a look at number 14, please. It says this, the diagram shows current I flowing in a circular coil located in a magnetic field, and those X's means the magnetic field is going which way? The magnetic force acting on the coil, you know what? Put a little positive right at the top. Which way will that positive right there feel a force? Put a little positive right here on the left. Which way will that positive right there feel a force? Put a little positive right here. Which way will that positive right there feel a force? What's this ring going to do? A, B, C, or D? And I will actually show you a video in just a second of a quarter going through this, and you will actually see the quarter shrinks. Okay? I will show you that.
I want to see that video.
So 14B. $15 is good. Lyndon, just hang on. You can cross out 16. lost all my questions. Let's come back, Mr. Dewick. You can cross out 17. 18 is good. Lots of right-hand rule questions. 19 is good. 20 is good. 21 is good. 22 is good. 23. Cross out 24. 25 is good. 26 is good. 27 is good. 28 is good. 29. 30. Cross out 31. Cross out 32. Cross out 33. 34 is good. You don't need to worry about the scholarships. I'm going to be giving you one combined test on all the magnet stuff, so that's part one. We're going to continue on with this some more. Okay?